Thank you, Thomas. So today we have Dan Camps from LBL NERSC. He's gonna talk to us about their work there. And if we have a little bit of time at the end, we're gonna give an update on the Linux Foundation pursuit that we're going over, we're trying to do. But for now, I'll hand it over to Dan.
Thank you, Amir. I do expect that there might be time at the end of the talk. I have prepared roughly 20 slides, so feel free to interrupt me at any point if there's questions during or after the talk. And happy to discuss. So like Amir said, I'm Daan Kamps. I work in the Advanced Technologies Group at NERSC at Lawrence Berkeley National Lab. And today I'm going to talk to you about a white paper that we released in September from last year on the archive, where we looked at different kinds of use cases that are relevant to our center and quantum computing technology roadmaps and how they come together in the next couple of years. So this work was done with a lot of people on our team at NERSC. So I believe many of you probably already know Ermal, Katie, and Brian. I think they're members of openQSE. Then we also work with Kevin, Jan, Nick at NERSC last year, and then Siba was a postdoc, and Youngjin, a grad student, worked on various parts of the white paper. So to get started with a high-level summary of what we discuss in the document, nothing probably too surprising if you've been following quantum computing and quantum algorithms for the past couple of years, but we're seeing rapid progress in the field, both on the theoretical/algorithm side, with algorithms and resources becoming ever more efficient, as well as on the hardware and the entire stack side, that computers are getting significantly better over time. Based on the data we analyzed, which was all published and public data, we project within the next 5 years an overlap to appear between capabilities of current contemporary quantum computers and resources that people expect will be required for solving potentially hard problems in quantum physics and chemistry. There's natural risks associated with these projections and predictions, as you may expect. They predict orders of magnitude improvements, both in gate depth as well as in number of logical qubits. The key there to realizing this will be to transition to scalable or corrected architectures. In this time frame, it seems, based on what we found, that and depending on the technology, that the speed of the quantum computer can impact feasibility as a secondary KPI beyond just pure error rates. And to capture that, we proposed a quite simple metric, which is derived from previous metrics that NERSC has put out there to study performance of supercomputers, which we're calling SQSP, which stands for Sustained Quantum System Performance, and it tries to capture the system level throughput for a heterogeneous workload. So I'll discuss about all of these separate parts in the remainder of my talk. But before diving into the details, the reason that we did this work last year and we're actively interested in this topic is because since the last few years, we've been updating our roadmap. We're currently at the NERSC 9 system, Perlmutter, but we have actively started working on NERSC 10, and there's an early access system in our data center with the full system coming later this year and next year. But we have been targeting the system after NERSC 10, which will be NERSC 11, to have a quantum computing component. So with which each generation of supercomputer, we bring in new capabilities into our organization and make it available to our user base. And quantum computing, we really envision to be a key metric of success for the NERSC 11 project, which is scheduled for the first half of the next decade, early 2030s. So to be prepared for that, we're doing the groundwork today. And why we're planning to have a quantum computer as part of NERSC 11, and part of NERSC offering is because our workload it's very diverse, but a huge chunk of our workload aims to solve problems that are quantum mechanical in nature, some kind of quantum many-body problem, often with classical approximations such as DFT and lattice QCD. But the underlying problem that the researchers aim to solve or simulate is a quantum many-body problem. And for many of those, there are quantum algorithms developed in the literature, quantum resource estimates available, and then there's even like types of applications that are not necessarily quantum mechanical in nature, such as solving linear systems, solving PDEs, where people have analyzed quantum algorithms. They are typically a little less mature than maybe the physical sciences applications. So we'll be focusing mostly on those, and in particular on material science, condensed matter physics, chemistry, and high energy physics. So this slide is the kind of a takeaway message from our white paper, and it tries to argue that we can expect such an overlap to appear between the resource estimates for hard computational applications and what quantum computers are projected to be able to do. So in this plot, which has a number of qubits on the x-axis, and it goes from like just a single logical qubit up to like many tens of thousands of logical qubits, and then the circuit depth on the y-axis. We see these lines. They show the projections that the vendors are saying they'll be able to do now in 5 years and in 10 years down the line, and then the rough areas where the different types of application areas have the most promising resource estimates. And these start to overlap in the next 5 to 10 years. So this is an encouraging sign that everything seems to align within this time frame. How do we come to this plot, which is what I'll discuss next? So we surveyed all vendors that we could find in on the web and in the literature that are building quantum hardware and that have a kind of public technology roadmap, as well as the literature on quantum resource estimation, particularly in condensed matter physics, in chemistry, and high energy physics. And then in our methodology, we prioritized unifying all the data we found against a single, quite simple metric, which is this qubits versus circuit depth. With such an endeavor, there's a whole list of caveats. I've listed some here. Different papers can have different underlying assumptions. Different roadmaps can have different underlying assumptions. Not everyone takes into account all the overhead for routing and resource state generation. Often it's only leading order resource estimates. There may be unknowns that we'll only find out later that are still unknown today. It could be that, we've only based this on public data. So there could be, there likely vendor internal data that is more precise than what's publicly available. Different vendors and different papers can have a different level of optimism, things like that. So there's a variety in the data set that we've collected, and we try to unify it against a single metric. So the first part of the question then is like, how large of a quantum computer will we need based on the resource estimates in these application spaces that we're interested in? So to address that question, it's quite useful to introduce the topic of quantum resource estimation. Many of you may be familiar with it already, but it takes all the steps starting from a domain problem in chemistry or physics, finding or mapping it to a quantum algorithm, ideally taking into account the initial state prep cost, any and post-processing required, and then map it to the relevant quantum resources, typically a quantum circuit expressed in some discrete gate sets, such as Clifford plus T, and distill some high-level statistics about the circuit. The most basic form would be the number of qubits and number of gates, often the number of non-Clifford gates in such a circuit. So from these resource estimates, we we distilled these two data points, the qubits and gates, and we called it in our white paper the P vector. And we surveyed the literature for this kind of data and collected in total over 140 resource estimates from these three different types of domains. A very well-known resource estimate that is arguably probably the most well-developed one is the FOMOCO case study in quantum chemistry. So for those of you that are not aware, this is a cofactor of an enzyme called nitrogenase that catalyzes nitrogen fixation, which is a process that occurs very, very efficiently in nature, thanks to this reaction that we don't quite understand. But we replicate in industry to produce fertilizer. And it requires quite a lot of energy to do so with the current processes. So an improved understanding of the chemistry going on in this system could help save a substantial percentage of the world's energy demand. For all these reasons, it has become kind of the poster child of quantum chemistry, quantum algorithms, and it has become a real benchmark problem. Over the past 5 to 10 years, there's been a variety of papers that have tried to improve and gradually reduce the cost of solving this problem with quantum computers to great effect, like ever better quantum algorithms, better techniques to encode it, to simulate it on the quantum computer have reduced the gate requirements by 3 orders of magnitude, while also simultaneously reducing the qubit requirements by close to an order of magnitude. So this is a real space-time volume reduction of the actual quantum computation. Beyond this single case study of FOMOCO, we include about 30 other resource estimates for quantum chemistry in the white paper. For condensed matter physics, we collected a total of 80 plus resource estimates, and here we see mostly as applications quantum dynamics, either using Trotter or some type of qubitization, and ground state energy estimation and preparation using quantum phase estimation. Some key problems that stood out during the lit review was that people look at discovering or simulating new cathode materials for lithium-ion batteries or studying some exotic phases of quantum matter. And the plot here shows all the data we collected, split down by the different types of algorithms. So we do see a lot of quantum phase estimation, either with Trotter or with qubitization, or some dynamics use like I mentioned before, using Trotter or qubitization. These seem to be the key workhorse algorithms that people have studied in the literature. And then the final category that we looked at was high energy physics. This was mostly done by Ermal, this part of the study. So here we looked at ways of doing simulation of the Schwinger model, neutrino oscillations, and then some heavy ion simulations as examples. There are similar algorithms appearing here, such as qubitization and Trotter, but a couple of others as well. One thing that stands out here is that the resources required are in generally much higher compared to chemistry, and definitely compared to simulating Heisenberg models, which we attribute to like a variety of factors. One aspect is that some of the models are a little bit more complicated. They have more terms that you need to encode and implement. Potentially, their scaling is a little bit different, but also there has been less push to fully optimize these models and these estimates in the literature. So these could come down, similar to the FOMOCO benchmark, if enough further work has been done. So this summarizes like the 140 plus estimates. We kind of simplified the picture by categorizing in these three wedges. And like I talked before, we see that high energy physics seems to scale the worst. It requires the most gates, gate depth, circuit depth, the highest encoding overhead, and like mentioned just before, we can partially attribute this to the algorithms maybe being a little less mature compared to quantum chemistry, where people have really optimized the way they do these block encodings and factorize the Hamiltonian. And as a consequence of that, the resources for quantum chemistry are significantly lower, although higher than like simulating maybe lattice models, because they can often map quite naturally to qubits without having any overhead for doing like a Jordan-Wigner or whatever kind of encoding you need to do for fermions. So that's the high-level picture that arises from our literature review for the applications. Then moving on to the review of all the public vendor roadmaps, we try to ask ourselves what quantum computers can we expect, and we found in total 10 public technology roadmaps that had sufficient data to derive a p-vector estimate from the public data. 6 of those were companies building superconducting qubits, 2 trapped ions and 2 neutral atoms. And we did our best effort to unify the milestone data according to this p-vector. And we took into account some optimistic scenarios of what quantum error mitigation and quantum error correction could have on the hardware performance. So with that methodology in mind, here's one example of data we collected. This is example data for IQM, where we found a whole list of systems they have on their roadmap from 2024 all the way out to 2033. We try to categorize them in terms of like whether they're like operating fully in NISQ mode, or are scalable fault tolerant devices, or fall somewhere in between where we label them as early fault tolerant. And then we have a number of qubits, both physical and encoded qubits. And for all vendors that we have a p-factor, we have some proxy for max depth, either error or the vendors report maximum gate depth on their roadmap. So that allows us to generate a plot that looks like this for every vendor. And consolidating the 10 vendors in a single plot gave this plot where the markers show the individual milestones separated out by type of qubit technology. The purple circles are superconducting, all superconducting tech milestones. Then we have the ions and the atoms. And then we've demarcated these lines, which go to the milestones, the best milestones today, in 5 years, and in 10 years. So this is the most optimistic scenario that is being made publicly, and that gives us these bounds on performance in that time frame, which brings us back to the plot we saw at the beginning. In the most optimistic scenarios, we do expect a significant overlap to appear. In maybe less optimistic scenarios, we may have significantly fewer overlap, and maybe close to none. So there is definitely a need of filling in this gap in between where we are today and where we need to be for the resource estimates. So there's a need for better algorithms within all these 3 of the domains, and most pressingly probably within high energy physics. There's a lot of opportunity to improve there. And the final question we asked, I'm almost at the end of my slides already, so if you have any questions about what I've talked about thus far, happy to pause for a minute.
We have Namit has a question. Here.
Yeah. Hey Dan. Have you, in your research estimates, have you considered partial FTQC estimates for anything?
Not directly. The closest what we have considered is allowing on the hardware side, we gave an optimistic scenario, which are these grayed out zones here in the plot, where we consider the scenario of combining quantum error mitigation with quantum error correction, where you would increase the sample overhead, but you could potentially increase the space-time volume that you can still get a signal out of.
Right. Yeah, in a certain sense, that is a parallel to what you do with partial FTQC, even though not quite the same, right? But for Fermi-Hubbard, for 2D Fermi-Hubbard, for example, we worked on this thing where we reported 10 to the 5 and even lower on 10 to the 4, higher on the 10 to the 4 physical qubits for 2D Fermi-Hubbard and trotterization algorithms. So it's just one of those problems where managing the sampling overhead and basically the depth of your circuit leaves you with like a sweet spot. And for some class of problems like 2D Fermi-Hubbard,
do you know what lattice size that was, or does it depend on the lattice size?
It does depend on the lattice size. It can go up to 10 by 10, 12 by 12, which is not quite where you want to be, but it's good enough for you to start seeing the finite size scaling that you need to get the thermodynamic phases. And yeah, so that's just something to think about.
Yeah, no, that's a great comment. I'm sure like people like you and algorithm developers out there can come up with all kinds of new ideas to bridge that gap and bring the estimates down. So that's great.
Right. And then, maybe there is some room for doing this with the HEP with high energy physics problems because those counts have always been a bit too high for comfort.
They've been quite scary thus far.
Yeah. Great. Thanks.
Yeah.
Hi, this is Yuri. Could you talk a little bit about sort of the normalization and the reduction of the circuit size and complexity of algorithms? So 2 parts, 2 questions, if you will, or 2 parts. First, so you're assuming logical qubits, obviously, and the kind of a universal gate set, or what is sort of the normalization for the circuit depth?
Right. So we did our assumption often explicitly, sometimes implicitly, was that we normalize everything to a Clifford plus T gate set. If the resource estimates were reported in thoughtfullies, then we did the naive conversion of like 1 thoughtfully you can implement with I believe 4 T gates. So we use that conversion factor.
Okay. And second question, like, obviously there's a lot of development, or advancement in algorithms to reduce, optimize and reduce the gates, right? So I think, in the first example, you talk about sort of, if I remember correctly, like a 5x reduction, and I forget the dimension if you don't, yeah. So could you speak to that and kind of, have you looked at the expectation of improving algorithms and reducing the, naturally through algorithmic improvements, right, exactly, right? So 1000x qubit and 5x. Right?
Yeah, that's I like this is a guesstimate more so than founded on like hard data, but it seems to me, based on like reviewing the literature and the state of literature, that like a lot of effort has gone into optimizing like these encodings for electronic structure problems. So I would expect that a lot of the low-hanging fruit there has been discovered and done. So it might be harder to come up with like another 1000x reduction in that space, although you never know, it's hard to predict the future. But I think there's more room in high energy physics and potentially like ab initio materials.
Right. Yeah, and this is very interesting work, right? And this is very hard predicting, right? Because as you said, you can predict the future with the algorithm discoverable. But I think it's interesting that you look at the dimension, maybe future, explore this more, because there's the push from technologies and and vendors, and there's the push down, right, from the improvements and understanding more of the problem and experimenting with actually even with NERSC era computers to figure out what that would be, right? So
exactly,
looking forward to hearing more about that, right? Because frankly, it will take a while to build the technology, right? 5-10 years. I think that there's potentially more there, even though, as you said, it's a very active area. So hopefully there will be some further improvements, even though as dramatic or impressive as this.
Yeah. Like it's a different type of application, but like in recent months, all the the results that have come out for like optimizing Shor's algorithm on neutral atoms or different types of architectures, they seem to be able to find a lot of gains still. So like I wouldn't be surprised if some similar things can be done within the sciences as well.
Thank you.
Okay. So another question.
So yeah, so I have a question. Did you consider kind of the variations with respect to noise model when someone is accounting for the overhead in FTQC? So if you consider hardware that, let's say you assume that median gate performance versus the worst case, like or the tail of the distribution, there's a big difference.
Yeah.
And we studied that it could be a factor of 5 to 10 in the number of physical qubit, more, and another like order of magnitude also in the number of gates T gates you need. I think some of the assumptions, for example, with respect to people completely ignore the correlated errors like crosstalk, background radiation, TLS for superconducting qubits. There could be similar correlated errors for neutral atom. Like people mischaracterize or like underappreciating the noise models factor into the resource estimate.
Yeah, I fully agree with that comment. I think it's an aspect that has been underappreciated, partially also because it's challenging to study probably. It will probably mostly affect on our plots like the lines more so than the resource estimates, like what the actual hardware is able to run. And it could turn out that some of the projections of the vendors are overly optimistic because they don't take into account all sources of noise in their modeling.
I don't necessarily agree that this only changes the line, but it just actually moves the dots. So what I'm saying is that once you do resource estimate, you're making some assumption for what kind of code distance you need and kind of how much, basically what's overhead in your FTQC versus like a physical layer, and that the noise model goes there. So I'm saying that if you have a probability distribution for errors, instead of considering the median performance, that's just not an indicator. You're just making a wrong resource estimate rather than it's just not the hardware is going to always have the distribution of qubit code fidelities. They're not uniform. And so it's you could say that this is a wrong assumption about the gate fidelity. I'm saying that it's not about what gate fidelity reports, it's what it means when they send you like a set of numbers that characterizes their system. It's not what the resource estimate community think it is. It's just they have a different objectives to get like VC funded kind of things for their roadmap. They're not necessarily worried about that resource count.
Yeah. Thank you for the comment.
Okay, thanks. So
the final part of the white paper and the presentation, we looked a little bit at throughput and speed of the quantum computer. We also applied a relatively simple model here to do the analysis. So we proposed this sustained quantum system performance metric, which is an analog of a metric that was originally proposed in 2005 at NERSC, sustained system performance, and has been updated by colleagues at NERSC to modern supercomputers that are heterogeneous systems with both GPU and CPU partitions. So this is something NERSC actively uses in evaluating and comparing like hardwares. So we thought about what an analog could be in the quantum space, and the way that they have typically analyzed the throughput for a heterogeneous suite of benchmark applications is by considering the geometric mean of all execution times. It's more robust to outliers, and it has been used within our organization, so it makes sense to compare to classical compute as well with a unified metric. So we looked at this and we used logical clock frequency, where we assumed a serialized resource state generation as a proxy to estimate throughput for systems at different scales and at different speeds. And under this arguably quite pessimistic assumption, it's likely that resource state generation can be parallelized to a certain extent, although it's maybe application dependent how much you can benefit from that. But this is a baseline estimate. We see that like back of the envelope, like at like the scales that we're targeting, like the clock frequency will have to at least be on the order, like at least be high enough such that the throughput doesn't become negligible. And this is like the number of allocations you could solve in a year. And we see that if you could only generate like 1,000 resource states a second, and you want to run gigacop scale, you can only run like at most 2 applications a year, which is very low compared to the usage and the number of users and throughput we see on our classical supercomputers that are used by over 10,000 people a year for over 1,000 projects. So it sketches a very different picture. So speed is definitely going to be next to error rates and gate depth a key KPI for these kind of systems. So that was everything I had for today. So this just repeats the initial findings I had up on the slide. So I'll leave this up for discussion, but I'm happy to take any more questions.
Thanks, Dan. Any questions? I have a couple simple ones, but so when we talk about quantum resource estimation here, when you do the resource estimates, did you actually use any tools, or did you develop any tools for the resource estimation, or did you rely on the
what we did in this work was
literature?
just a lit review. So we collected everything from the literature that we could find. We checked their assumptions to a certain extent, but we didn't reproduce every resource estimate for this paper. But there, if you're interested in that field, there's multiple software packages out there that people have developed, such as out of Lincoln Labs. There's PyLitiker. There's I think Google has their own tool. There's a few packages out there that you can use.
Okay. And have you guys looked, or are you currently looking at not only resource estimation for the quantum workload, but also the HPC? Like when we talk about HPC QC integration, are you looking at the entire picture of what like an application would need from the HPC side as well as the quantum side?
We've definitely had like discussions along those lines, and we're talking to users to try and map that out. But no, we don't have like a paper out on that yet. Maybe
Go
Arnold.
Go ahead, Mr.
Yeah. So just following up on the Amir question on the HPC requirements. So there are kind of various requirements that one has to consider is like kind of for lower layer of stack assumptions on the latency and throughput for like, let's say, real-time decoding, but also at the high level of application, let's say for workload management or even application pipeline. What are like, you know, do you have any conclusion on the kind of weak coupling versus strong coupling in like, and even distributed quantum computing? What are the requirements for networking?
Yeah. So we looked at a couple of years ago, we looked at the decoding problem. We had a paper in 2024 that analyzed one type of decoder and how it could scale. That's probably due for an update, that kind of research. But there we concluded that like scaling it up to these types of problems we're discussing today may require a few racks of classical compute, depending on how efficient you can stand that system up, but it has to be closely coupled to the quantum computer in terms of like the workload management and pre and post processing data. To us at the moment, it seems that latency is much less of a requirement there. The data, the actual data that they produce at the end of a computation is relatively limited for these devices, and their throughput is expected to be also not tremendously high, as we discussed before. So I think there is quite a bit of the requirements there are not that strict, is our current thinking.
Yeah, but you have to consider that this is based on the algorithms that are designed to showcase the quantum GPU performance, not the HPC performance.
Yeah, there may be applications or workflows out there that do require it, and if you come across these, we're very interested in learning about them. Definitely.
Yeah, we can talk about that. Yeah, so basically, I'm saying there is this kind of inductive bias. Quantum computing community, they just want to like create that quantum advantage, and they study workloads that is just less intensive classically, and just you can get maximum kind of output from a standalone QPU, even like remotely connected.
Mm-hmm.
That just intrinsically the community has been on that track for a while.
Yeah.
But that doesn't mean that's kind of those are the only opportunities. Yeah. Okay, thanks a lot. Nice presentation.
Anybody else has any questions, comments? All right, maybe I'll spend 5 minutes. Oh, sorry, we have like 2. Masoud, do you want to say something?
No, it was, yeah. I'm done.
Okay.
Thanks.
Yeah. So more of a comment, right? So I like your drawing analogy from kind of the classical world, or I come from the classical world as well. And so 2 things. I like the mean value analysis kind of aspect, right? There's a lot of details in the sort of resource estimation and nonlinearity of stuff. But I think the fact that you look at mean value as the common denominator, although we all know about distributions and the fallacy of mean and median, but I think that's very nice. And second thing is that kind of like maybe have you looked at sort of a designing like a closed loop throughput model, right, where sort of in your work, if I had to understand correctly, you estimate or you assume that the HPC portion is in the bottleneck, the pre and post processing, that sort of the bandwidth requirements for the results coming out of computer are fine. Have you thought about expanding kind of a throughput model kind of from the performance analysis of the 80s and 90s work, even from the mainframe days, where sort of you have stages, you have queues, and you have kind of harking on the kilohertz, megahertz, gigahertz kind of assumption of the clock speed, if you will, of the QPU state.
Yeah, I looked into that for a little while, a couple of years ago. I never really got to any main conclusions out of it. It would be an interesting idea to explore further. I definitely agree with that.
And again, I mean, we can talk offline. I don't want to sort of monopolize, but I what I really like about your work is that it's very hard to normalize and predict the future based on different vendors roadmaps and things. But I think the fact that there's a lot of operations research that has been done for mainframes, and largely this kind of has the mainframe-ish look, right? If you scale back, it's I think really good, because there's a lot of good work and research and solvers that kind of ignore what is the service center, and kind of you have the clock speed, you have kind of the requirement of how many qubits and how many gates, and you can associate the classical GPU requirements with sort of the thing. So anyway, we can talk offline or
definitely. I think there's interesting ways of building more complicated models and better models. Yeah, thank you.
Yeah.
Any other questions, comments?